let's talk about equilibrium. Torque and equilibrium. The first condition for equilibrium is that the net external force must be zero. There should not be any force that is acting on it that is accelerating it. Now, the important thing to remember is the net force on it is going to be zero in any direction. So that means sigma fx has to be zero and sigma fy has to be zero. And if we are talking about three dimensions, then obviously sigma fz also has to be zero. This is a necessary but not sufficient condition to ensure that an object is completely in mechanical equilibrium. So this is a statement of translation equilibrium. Now, what will make the second condition of equilibrium be true is that the net external torque must also be zero in order to achieve equilibrium. So this is a statement of rotational equilibrium. So in order to have equilibrium in any system, we need both of these conditions to be fulfilled. Sigma ff has to be zero, which is the sum of all forces has to be zero, and the sum of all torques also have to be zero. So now let's look at an example. A sign is supported by a uniform horizontal boom of length 3 meters and weight 80 newtons. A cable inclined at 35-degree angle with the boom is attached at a distance of 2.38 meters from the hinge at the wall. The weight of the sign is 120 newtons. What is the tension in that cable? And what are the horizontal and vertical forces exerted on the boom by the hinge? So we are looking for the forces that are acting on the boom by the hinge. Okay, so now let's walk through this problem. It says that we have a sign that is supported by a wall, and that sign is hung over here, and it is 120 newtons. And it also gives us the fact that the length of the system is 3 meters, and the weight is 18 newtons. And it says that the cable that connects it to up here is at an angle of 30 degrees. So the cable angle is 30 degrees. And the tension is going to be pointing upwards. And it says it is at a distance of, so the distance is going to be 2.38 meters. Okay? And then it says that the sign weighs 120 newtons. And what we need is, this is for the boom, this is for the cable, and for the sign, the only thing that is given to us is its weight, which is 120 newtons. Okay, so this is all the information that the question is giving us. Now, what do we need in order to solve this? What we are solving for is the tension, and we are solving for forces, right? So I'm going to call them N. So in order for me to be very careful, I need to solve for Nx and Ny. Okay, so now that I know what my question is asking me, I can start tackling what I need to do. So this system is in equilibrium. That means in order to fulfill this, I should have sigma F be equals to 0, and sigma torque should be equals to 0. Now these are going to be very, very useful for me to be able to solve all of the requirements that I need. Okay, so let's look at the first one. When I look at my force equations, how many force equations should I have? I should have a sigma Fx and a sigma Fy. Agreed? And since they are both in equilibrium, they should both be equals to 0. But now let's start looking at how many multiple different things we have. Well, we have a normal force that acts outwards. We have a upward force that I'm calling Ny. Then we have the weight of this, and then we have the weight of, let's call this the weight of the sign and the weight of the boom. Okay, so these are all the forces that are acting on it. So in my x direction, I have a tension force, and then these can be reduced further into components. This is going to be T sine theta, and this is going to be T cosine theta. So I'm going to have a minus T cosine theta plus nx. I am considering my positive axis to be this way. Okay? Now, in my y coordinates, I'm going to have a t sine theta. I'm going to have a weight due to the bar. I'm going to have a weight due to the sine. And I am going to have a normal force that is acting upwards from the hinge. Okay? Now that I have my force equations, I can easily put this equals to 0 and this equals to 0. Why? The reason why is because I know that this system is not moving. It's in equilibrium. Okay, so this means from equation 1, we'll call this equation 2 and equation 1. So from equation 1, I have t cosine theta equals nx. And from my equation 2, I will get t sine theta equals weight of the bar plus weight of the sine minus ny. So this is going to be the result of 1, and this is now going to be my number 2. Okay, so this is good. Well, I still don't know tension. I need to find tension, I need to find nx, and I need to find ny. What to do? Well, in this case, let's look for what we already know. So I'm going to call this one B. So now let's do the sum of the torques. If I do the sum of the torques, how many different objects are acting on it? Well, I'm going to call my hinge to be the point that I'm looking at, so I don't have to worry about nx and ny. So in this case, I will have a torque due to the bar, right, which is acting right here in the middle. Then I will have a torque due to the sine, which is acting right here. It's also pointing downwards. And I will have a torque due to the tension in the cable. So I'm just going to call it tension in the cable, right? So now I have all of my forces done. Am I missing anything? Since I moved my axis of rotation to be here, and x and ny go away, I don't think I have anything else. So I'm good. Now what about plus and minus signs? Do you notice I don't have any plus and minus signs? What do I do in that case? Well, I look at the forces. This is a downward force, so it's going to cause the system to accelerate that way. That means this is going to be a negative torque. Sine similarly goes downwards. That means it's going to be a negative torque. Cable tension is upwards. Both of these angles are upwards, so that means I'm going to have a plus coordinate in that case. Now, this is going to be 0 because it's in equilibrium. It's not really going anywhere. So that takes care of that problem. What am I left with? I am left with the torque in the bar and the torque in the sine and the torque in the cable. Now the answers to those ones, if you remember, torques are always R times F. Right? So for the bar, since this is going to be the length for R, it is going to be L by 2 times the weight of the bar. Okay, times sine of theta, and the angle is going to be 90 degrees. Okay, minus, for the sine, it is going to be the total length times the weight of the sine. Right? Plus the tension in the cable and the distance that it gives me. Okay, all of these are going to be equals to 0. Now, I know the L, I know the weight of the bar, I know the weight of the sine, I know the distance of the for the tensions. All I need to do is plug in the numbers and calculate. Go ahead and do that. I've calculated it to be equals to 352 newtons. Okay, so your homework is to actually plug in the values and see if you get the same answer as I do. If not, then we're going to be in trouble. Oh, TD sine of 30 degrees. Sorry, forgot the sine of 30 degrees. Now that I have tension, can I calculate nx and ny? And the answer is absolutely. So I will have to go back to my equations 1 and 2 and plug in my tensions in these two expressions right here, where the theta is given by 30 degrees. And if you do that and you plug in all of the other numbers and everything that you know, you will get Nx to be equals to 288 newtons, and your Ny to be equals to minus 2 newtons. So please go ahead, make sure that you solve and you plug in all the numbers yourself and make sure that what my calculations are actually correct. Don't trust them. Do it for yourself. Because being human, I can make mistakes.